Yes, it is feasible.
Okay. So this is lecture 6, principal components analysis. We have an introduction. The main objective of principal component analysis is to reduce the dimension of the observation. So if we have so many observations, then you can reduce the dimensions of this observation. This is the main objective of PCA, that is the principal components analysis. The simplest way of dimension reduction is to take just one element of the observed vector and then discard all others. This is not very reasonable approach because information may be lost. So principal components analysis turns to reducing the dimension of X through linear combination of its components. So instead of picking only one element and discarding the rest, then you reduce the dimension of X through a linear combination of the components of X. That is, you are searching for a linear combination with the largest variances. So in principal component analysis, we need to compute the eigenvalues in the eigenvector. An eigenvalue is a square matrix. Of a square matrix is a scalar that is usually represented by a Greek letter lambda. And an eigenvector is a non-zero vector which is associated with each corresponding eigenvalue. Every eigenvalue and eigenvector X satisfy the equation. So we have matrix A times the eigenvector gives the eigenvalue times the eigenvector for any given square matrix A. So the definition of eigenvalue and eigenvector, that for a square matrix A of order n, the number lambda is an eigenvalue if and only if there exists a non-zero vector X such that this equation is satisfied. So in this case, X is called an eigenvector corresponding to lambda, and the pair lambda and X is called an eigenpair of the square matrix A. So when we use matrix multiplication properties, then we obtain, if you multiply the square matrix A minus lambda times I, all this multiplied by the eigenvector X equals 0. So this equation, it's a linear system for which the matrix, this is in form of a matrix, for which this matrix, then we also know that this system has only one solution if and only if the matrix is invertible. That is, if you can determine the determinant of this matrix A minus lambda times the identity matrix of A. So if the determinant exists, then the matrix is invertible. So the zero vector is a solution and X is not the zero vector. Therefore, it means that the determinant of A minus lambda I equals 0. Example, if you consider this simple matrix, A is 1 minus 2 minus 2, 0. In general, or for a square matrix A of order n, that is the equation which will give the eigenvalues of A. So if you solve this equation, then you'll get all the eigenvalues of A. This equation is called the characteristic equation of A, and it is a polynomial function of lambda of degree n. So we know that this equation will not have more than n solutions. So we'll only have up to n solutions. We have the properties of these eigenvalues. Given a vector X, a random vector X with the corresponding covariance matrix sigma, and the eigenvalues, so the first eigenvalue must be greater than the second eigenvalue, which is greater than the third, up to the pth eigenvalue. Then we have the property that summation of sigma ii will give the sum of the eigenvalues. And then another property is that the determinant of the covariance matrix will be the product of the eigenvalues. So an example to prove these two properties, that is the sum of sigma ii, is that is the diagonal matrix of our covariance matrix A, matrix sigma, is the sum of the eigenvalues, and then the determinant of the covariance matrix is the product of the eigenvalues. Example, let X be normal with mean mu and dispersion matrix sigma. This be a trivariate normal vector where we have S is given by this. Just a moment, I pick a call. Okay, let's continue. So if you're given this, X is a trivariate normal vector, and we're given S as this matrix, find the eigenvalues and the eigenvector which corresponds to the first eigenvalue. So here we have that S is given by that, so we need to solve the eigenvalue. For the eigenvalue, we solve the characteristic equation, that is A minus lambda times the identity matrix equals 0. This is the same as, so we are subtracting our A minus our lambda times identity matrix. So we have that 1, S is our A in this case, so we have 1 minus lambda, then the 0, then 0.6, then 0, 4 minus lambda, 0, 0.6, 0, and 9 minus lambda. So we solve this characteristic equation equate to the 0 matrix. So solving this will give us the eigenvalues of this matrix. So to do this, then we have the determinant of this matrix. We can have this as this row. So we have 1 minus lambda. So if you remove that, then you multiply by the determinant of this other matrix, that is 4 minus lambda times 9 minus lambda. Then we have, this is 0, so we can ignore that. That will give a 0. Then for 0.6, so we have 0.6 multiplied by this, so we have a 0, and that's why we have a negative minus 0.6 times 4 minus lambda. So 0.6 times 4 minus lambda, we equate this to 0. So 4 minus lambda is common. 4 minus lambda into 1 minus lambda times 9 minus lambda minus 0.36 equals 0. So we know that here we have 4 minus lambda equals 0, or 1 minus lambda 9 minus lambda minus 0.36 is also equals to 0. So from here we get three values of lambda. So we have lambda 1, that is the largest, is 9.0447. Lambda 2, the second largest, that is 4. And lambda 3 is 0.9553. So to obtain the eigenvector, so we already have the three eigenvalues. To obtain the eigenvector which corresponds to the first eigenvalue, so that will be eigenvector E1, which is E11, E12, and E13. So to obtain this, we solve the equation. Here we are replacing the lambdas with the value of lambda 1. So we have 1 minus lambda 1, here 4 minus lambda 1, and 9 minus lambda 1. But lambda 1 is 9.0448. So we have 1 minus 9.0448 is negative 8.045. Then here we have 0.604 minus lambda 1, that gives 5.045, and then we have a 0.60, and then here we have negative 0.045. So this is multiplied by E11, E12, E13, and then we equate to 0. So solving this equation, so we can have the first equation, that is negative 8.045 E11 plus this, the second term is 0 for E12, so then we have 0.6 E13 equals 0. Then the second one, we have this, the second row, so that is 0, and then the second term 5.045 E12, and this is also 0, so this we equate to 0. And then the last one, we have 0.6 E11 minus 0.045 E13 equals 0. So from here already E12 is 0. And if E12 is 0, then we can use either this equation 1, which is 2, 3. So we can use either this 1 or 3 to get E1, to make E13 the subject. So we have E13 can either be 13.33 E11 from either this or this. Then this is subject to E1 equals 1. That is E1 times E1 transpose equals 1. That is the product of E11, E12, E13 times its transpose, E11, E12, E13. That product must be 1, meaning we have E11 squared plus E12 squared plus E13 squared equals 1. So from here we have that E13 is 13.333 E11. So we can get the value of E11, but we know that E12 is 0. So we have E11 squared plus E13 squared equals 1. So we have E11 squared plus our E13 is 13.333 E11. This is squared and this is also squared equals 1. Then from here we can get the value of E11, and the value of E11 is 0.045. 0.0748. Then now we can get the value of E13, which is 13.333 times 0.0748, and this gives 0.999978. So we have the eigenvector E1. This is the eigenvector corresponding to the first eigen value, and that is 0.0748, 0, and 0.999978. Then, because we know from the property that the sum of the eigenvalues must give us the diagonal matrix 1 plus 4 plus 9, which is 14. So again, if you sum all the eigenvalues, you also get 14. And then the trace of that matrix is also 14. The product of the eigenvalues gives 34.56. And also, if you calculate the determinant of our matrix S, we also get its determinant, we get 34.56. So hence, that the two properties are now satisfied, that the determinant of the matrix, the dispersion matrix, equals the product of the eigenvalues, and that the sum of the eigenvalues equals the trace of the dispersion matrix, or the sum of the diagonal matrix. Another definition is now the principal components. Now we know how to calculate the eigenvalues and the eigenvector. So given a vector x, x1, x2 up to xp transpose, be a random vector with the covariance matrix sigma, whose eigenvalues are lambda 1 up to lambda p. And remember, lambda 1 is greater than lambda 2, greater or equals to lambda p, which are all positive. Let yi, so we have a new variable, yi, be ai transpose x, and I is taking values 1 up to p. Then the variance of yi will be ai transpose sigma times ai, and the covariance of yij will be ai transpose sigma aj. Then the ith principal component is a linear combination of ai transpose x, which is now our yi. So this is the ith principal component, which maximizes the variance of yi. And this again is subject to ai transpose times ai, which is equals to 1. So in this case, this is our matrix X, a vector X, and this is the eigen vector. So that is the sum. We say that the sum of the squared coefficients, this add up to 1, and this new component, that is ai times x, the kth component, is uncorrelated with the previously defined components. That is, the covariance is 0. Then we have a theorem here that if the eigenvector pairs are given by this, then we have yi, which is the principal component, is the ith principal component. Then again, we have that the sum of the diagonal values is equals to the trace of the matrix, which is also the same as the sum of the eigenvalues. And therefore, the sum of the variance of xi will again be the trace of sigma, which will be again the sum of the eigenvalues. Therefore, from here, we have that the proportion of the total variance that is explained by the jth principal component will be given by lambda j, that is the jth eigenvalue divided by the total eigenvalues. So we have I from 1 up to p. So that is the proportion of variance that is explained by the jth principal component. Then we have another important quantity, which is the proportion of variance explained by the kth principal component. Sorry, the first k principal component. So for instance, for the first two principal components, then the proportion of variance they will explain will be the sum of the first two eigenvalues divided by the total eigenvalues. So that is the sum of j from 1 up to k lambda j divided by the total I from 1 to p lambda I. So this is the proportion of variance explained by the jth principal component, and this is the proportion of variance explained by the first k principal component. That is the first sum of the first eigenvalues of the k. If, for instance, if the first two principal components, then it's the sum of the first two eigenvalues divided by the total eigenvalues. And if this quantity is large, then we do not lose much information by considering only the first k principal components. So we have if y1, y2 up to yp are the principal components obtained from the covariance matrix sigma. So we can obtain p principal components according to the number of eigenvalues. Then we have another definition, is the correlation coefficient between that principal component and the kth variable. So the correlation coefficient between the ith principal component and the kth variable will be given by eik square root of lambda I divided by square root of sigma k times sigma k, which is the same as sigma kk. So this is the correlation coefficient between the ith principal component and the kth variable. So we can have an example on the same. You can follow through that and see how that works. Example, find the first principal component, the total variance explained by the component, and the correlation coefficient between the first principal component and the first variable based on the example above. So we had, for this example, we had already calculated the eigenvalues and the eigenvectors. So we have lambda 1 is 9.044447, lambda 2 is 4, and lambda 3 is 0.955553. Then we also calculated E1, vector E11, E12, and E13. This is for the first eigenvalues. And this gives E11 is 0.0748, E12 is 0, and E13 is 0.978. So the first principal component, Y1, will then be given by, let's use E. That is E1 times the vector X. So Y1 will therefore be 0.0748 that is 0.07480 E1 transpose 0 and 0.9978 times X1, X2, and X3. So this means that Y1 is 0.0748X1 plus 0.9, because the second one we have a 0, 9978 x3. So this is the first principal component. So from the first principal component, we get the first eigenvalue, then the eigenvector corresponding to the first eigenvalue. From the eigenvector, then we get the first principal component. Then the total variance explained by this first principal component will be the first eigenvalue divided by the total eigenvalues. And the first eigenvalue is 9.044447, and the total was 14. So we have that 64.61% of the total variance is explained by the first principal component. That is only 64.61 is explained by the first principal component. Then the other principal components will explain the rest. Then the next part is calculate, find the principal, the correlation coefficient between the first principal component and the first variable. So that is row of 1, the first principal component 1k, which is given by row of 1k root lambda 1 divided by sigma kk square root. So this means that we have the first principal component of the first variable. So we have row 1 equals E11, k is 1 because it's the first variable, lambda 1 divided by sigma 1. So E11 is a 0.0748, and then square root of lambda 1, our lambda 1, that is the first principal component, was 9.045, and then sigma 11 from this, sigma 11 is 1. So divide by square root of 1. That gives 0.22250. So this is how we calculate we get the principal, the ith principal component from the eigenvalues and the corresponding eigenvector of that eigenvalue. Then we can calculate the proportion of variance that principal component explains, and also we can also calculate the proportion of variance that is explained by the first k principal components, and then we can calculate the correlation coefficient between the principal component and the kth variable. So from here again you can calculate the second principal component. To calculate the second principal component, we replace lambda by 4. That is, lambda 2 is 4. So here we have 1 minus 4, 4 minus 4, 9 minus 4. Then we get E2, the vector E2, which is E21, E22, and E23. Then from here we can get the second principal component, which is E2 times x. That will give the second principal component. And again, you can calculate the third principal component by replacing lambda 3 in this equation. So there's some exercise on the same with the solution. Here we have that x is a trivariate normal random vector, and then the dispersion matrix is given by this. So here, first find the first two principal components, that is y1 and y2. The percentage of total variance they explain, that is the variance explained by y1 and also explained by y2, and the correlation coefficient between the second principal component and the first variable. So we have the solution. That was for the first exercise. Solution for this exercise, you can calculate the first two principal components, but for this solution, we only have a solution for the first principal component. So you can calculate the second principal component. So that is all under principal component analysis, unless there is a question before we move to the next, which is discriminant analysis. Any question? Okay, if there is none, then we can move to discriminant analysis. Discriminant analysis. This is a set of methods and tools that is used to distinguish between groups of population pi j, and to determine how to allocate a new observation into either of these groups or these populations. The situation here is we have two or more populations. So we have population 1, population 2, etc. up to population P. Possibly all are p-variate normal. Then the populations are known. So that means that we have data for each of this population. Then we have a new case, that is a new variable, for instance, a new variable x, that we want to identify which of these population this variable x belongs to. So this is what we call discriminant analysis. In general, we have population pi j, and we have to allocate an observation vector x, an observation x to one of these groups. A discriminant rule is a separation of the sample space into sets of Rj such that X is a member of Rj and it is identified as a member of population Ij. The main task of discriminant analysis is to find good regions Rj such that the error of misclassification is very, very small. So you might classify X in population 1 while it belongs to population 2, then that will be an error of misclassification. For example, we have population 1 and 2, and then we have the measured variables x1 up to xp. So we have good and poor credit risk. We can have income, age, number of credit cards, family size, etc. So you see which population to give to the values of these variables, income, age, etc. Another example is successful and unsuccessful admission to a course. So we want to allocate one of these into either of these populations. So we have entrance examination score, high school grade, number of high school activities, etc. Then the third example, purchasers and non-purchasers. So we have the variables income, education, family size, and occupation. So we want to allocate each of these variables into either of the two populations. Now suppose that the data from a new case X has a joint density function. So this new variable that we want to allocate into one of the population has a joint joint density function given by f of x1, x2 up to xn, or g of x1, x2 up to xn. So we want to make the decision D1 on whether to classify the case in population 1 or to classify the case in population 2. And if we classify the case in population 1, then we have the correct joint distribution is given by f of x. Or if you classify the case in population 2, then the correct joint distribution is g of g of x. Just like we said, there are two types of errors that you can find when you're trying to classify an observation X into one of the populations. So the first one is misclassification of the case in population 1 when it actually belongs to population 2. So we have P12, which is P. You classify it in population 1, that is, you make decision 1, P1, given that it actually belongs to population 2. So this P12 is the probability of this type of error. The second one, misclassifying the case in population 2 when it actually lies in population 1. Then we have the probability 2-1. So you make decision D2 given that it belongs to population 1. So this is the probability of this type of error, that is misclassifying the case in population 2 while it belongs to population 1. So this is similar to type 1 and type 2 errors in hypothesis testing. A discrimination scheme is defined by splitting the p-dimensional space into two regions. So we can split the p-dimensional space into two regions, R1 and R2, where R1 is the region where we make the decision D1. And remember, decision D1 is classifying into population 1. Then the region R2, where we make decision D2, that is classifying the case in population 2. So there can be several approaches to determine the regions R1 and R2, all concerned with taking into account the probabilities of misclassification. So you have to take into account the probability of misclassifying in population 2 given that it belongs to 1, and misclassifying in population 1 given it belongs to 2. So we set up the regions R1 and R2 so that one of the probabilities of misclassification, for instance, P21 is is at some low acceptable value A, and then accept the level of the other probability or the other misclassification, probability B. Then set up the regions R1 and R2 so that the total probability of misclassification, that is, probability of misclassification, is the sum of P1 times, that is the sum, P1, P21 plus P2, P1, P12 is minimized. So you want this total probability of misclassification to be minimized. Then set up regions R1 and R2 so that the total expected cost of misclassification is also minimized. So this is the expected cost of misclassification. Also, we want this to be minimized. So the maximum likelihood discriminant rule, there is a rule when you want to allocate an observation X to either of the population pi j. So denote the densities of each population, that is the probability density function, denote them by fj x, that is for population pi j. The maximum likelihood discriminant rule, which is also called the ML rule, is given by allocating x to pi j, maximizing the likelihood function. So you allocate x while you maximize the likelihood function xj. So we get the maximum of this. If several fi give the same maximum, then any of them may be selected. So mathematically, we are saying that we set region Rj given by the ML discriminant rule. This is defined as Rj such that Rj equals X such that the likelihood is greater than under J is greater than the likelihood under I. Or I equals 1 up to J and I is not equals to J. So by classifying the observations into certain groups, we may encounter misclassification error. For instance, for J equals 2, that is that only two populations or two groups, the probability of putting X into group 2, although it is from population 1, can be calculated as this. That is, you are putting X in population 2 given it belongs to 1, so it is the integral over region 1. And similarly, the probability, which is also the conditional probability of classifying into population 1, given that it belongs to 2, is that integral. And again, we can get the error of the expected cost of misclassification given by that. So we will be interested in classification rules that keep the expected cost of misclassification small or minimize it over the class of rules. The discriminant rule minimizes the expected cost of misclassification for two populations. For example, we have two populations given below. Given two populations, then the rule for minimizing the expected cost of misclassification is given by, we have R1 and R2. Such X such that we have probability under population 1 divided by population 2 is greater than this, and then for R2 it is less than that probability. Then the maximum likelihood discriminant rule is thus a special case of the ECM rule for equal misclassification. Sorry about that. I just lost my network. I hope this one will be stable. Can you hear me?
Yes.
Okay, in case you are not able to hear me, just let me know. Okay, let's continue. We have an example on the same. For two normal populations, we have population 1, which is from normal with mean mu1 and variance sigma 1 squared, and population 2, from the normal distribution with mean mu2 and variance sigma 2 squared. Then we have a variable x. The likelihood Lix will be, we know that this is the joint distribution, that is the product of the marginals, that is x1.
Excuse?
Yes.
I can't see your screen.
Oh, sorry. Let me present. Is it okay now?
Yes.
So we are saying that the likelihood of xi will then be 2 pi sigma I squared. That is sigma I squared negative 1 over 2, then exponential of negative a half x minus mu I over sigma I squared. So this is for each of the xi's. Hence, an observation X will be allocated to population 1 if L1, the likelihood under population 1, is greater than the likelihood under population 2. And now, if the likelihood and population 1 is greater than the likelihood and population 2, this will be equivalent to 1 population 2 divided by population 1. So the likelihood is greater or equals to 1. Now suppose that we have pi I is p-variate normal with mean mu I and the variance covariance Lopez distance between x and mu I, and this distance is given by this. So we have x mu I in the case when we have two populations, then we have that phi transpose x minus mu is greater or equals to 0, where this is given by sigma inverse mu1 minus mu2, and mu in this case is given by a half mu1 plus mu2. So to prove this, here we want to prove that when you want to classify in population 1, then that is when J is 2, we only have two populations, then we have mu1 minus mu2, transpose sigma inverse x minus mu plus a half mu1 plus mu2. So this is what we want to prove, that this is positive. So to prove this, now we have, because we have two populations, so we have population 1 and population 2, and both are from the normal distribution. So we have that L1, the likelihood under population 1 divided by the likelihood under population 2, will now be given by, we have 1 over 2 pi sigma squared. This is sigma power negative a half times exponential minus a half x minus mu1, that is the first population, transpose sigma inverse x minus mu1. Then this we are dividing by for population 2. So we have 1 over 2 pi sigma power negative a half exponential minus a half x minus mu2, that is from population 2, sigma inverse x minus mu2. So this and this will cancel. Then we remain with this exponential. So that we have exponential negative a half, that is for the numerator, x minus mu1 transpose sigma inverse x minus mu1. And this is greater or equals to exponential for the denominator minus a half x minus mu2 transpose sigma inverse x minus mu2. Then if you take logs on both sides, then the exponentials will go. So we remain with minus a half x minus mu1 transpose sigma inverse x minus mu1 is greater or equals to minus a half x minus mu2 transpose sigma inverse x minus mu2. So if we divide both sides by negative a half or multiply by negative 2, then this sign will of course change because we are dividing by a negative sign. So we'll have x minus mu1 transpose sigma inverse x minus mu1 is now less or equals to x minus mu2 transpose sigma inverse x minus mu2. If you open these brackets, then we have x times sigma inverse times x transpose. So x transpose sigma inverse times x minus x transpose sigma inverse times mu1. Minus, now for mu1 sigma inverse times x, mu1 and mu1, that is a plus, so we have plus mu1 sigma inverse times mu1. Now this is less or equals to this other side, which is again x transpose sigma inverse x minus x transpose sigma inverse mu2 minus mu2 sigma inverse x plus mu2 transpose sigma inverse mu2. This is sigma inverse mu2. So we have this term and this term will cancel, and if the two cancels, then we remain with for mu1 and x, we have minus 2 of them this and this. These are like terms. So we have minus 2 mu1 transpose sigma inverse times x. Then, so we already have these two terms. Then we add to this plus mu1 sigma inverse times mu1. Then on the other side, we also have minus 2, this, minus 2 of the same. So if you take it to this other side, we'll have plus 2 mu2 transpose sigma inverse x. Then we remain with this last term, which is now a minus mu2 sigma inverse mu2 transpose sigma inverse mu2. And now this is less or equals to 0. Then we have mu1 and mu1. So we can collect the like terms here. That is mu1 and mu2, this and this. So we have minus 2 mu1 minus mu2 transpose, then sigma inverse, then plus these other terms again. We have sigma inverse is common, then we have mu1 plus mu2 and mu1 minus mu2 transpose. So this is less or equals to 0. If we divide both sides by minus 2, again this will now change. Now we'll have greater or equals to 0. Divide both sides by minus 2. So we have mu1 minus mu2 transpose sigma inverse x minus, because we're dividing by minus 2, minus a half sigma inverse mu1 plus mu2 into mu1 minus mu2 is now greater or equals to 0. Then we have mu1 and mu1 minus mu2 is common. So we have mu1 minus mu2 transpose, and also sigma inverse is common. So here we are remaining with x minus a half mu1 plus mu2. This is greater or equals to 0. So this is what we want to prove, so we want to prove this part, transpose x minus mu is greater or equals to 0, where we have this as sigma inverse mu1 minus mu2, and this mu is a half mu1 plus mu2. So if you take these two here, then we'll have this is sigma inverse mu1 minus mu2. All this is multiplied by x minus a half mu1 plus mu2. So this is what we have just proved, that mu1 minus mu2 transpose sigma inverse times x minus a half mu1 plus mu2 is greater than 0. Then for the sample case, when it's a sample, then we're replacing the mu's with their corresponding MLEs, and also we're replacing this with the corresponding MLE. So we have x bar 1, we have x bar 1 minus x bar 2 S inverse times x minus a half x bar 1 plus x bar 2 is positive. So we say this is W. So if the value W is positive, that is if this term is positive, then we assign observation X to population 1. Otherwise, you assign it to population 2. And so if this value is negative, then we assign the object X to population 2. So this is what is referred to as the Fisher's discriminant function. We have an example on the same. So before we move to example, we have assumptions of discriminant analysis. We make a number of assumptions that the observations are a random sample and that they are normally distributed and that the variance are the same in each group. So this S is the pooled variance in each for the two groups. Example, given that x bar 1 is 1586 transpose, that is the mean, comes from population 1, and this x bar 2, 9, 15, 4 comes from population 2. So S is given by 9, 0, 1.5, 0, 8, negative 2, 1.5, negative 2, and 4. So use the discriminant rule to classify a new object X, which is 11, 13, and 3. So we are given that this mean comes from population 1, and this from population 2, and their variance, they have the same variance, which is given by that. So we need to classify a new object X, which is given by 11, 13, 3. You check in which population it belongs, whether it belongs to population 1 or population 2. So to do this, we need to know that the value of W is positive. If the value of W is think you lost me at one point. Are we together?
Yes.
We are together? Okay.
Yes.
Okay, so we calculate x minus a half x bar 1 plus x bar 2. So our x is 11, 13, 3.
Excuse.
9. Yes?
You can't see your presentation.
Oh, sorry. Okay, so we have x minus a half x bar 1 plus x bar 2. Our x is 11, 13, 3 minus a half over x bar 1 plus x bar 2. If you multiply this by a half, that will give 12, 11.5, and 5. After multiplying by a half, 12, 11.5, and 5. And this gives minus 1, 1.5, and minus 2. So we have from our formula, we have that W is x bar 1 minus x bar 2 transpose S inverse x minus a half x bar 1 plus x bar 2. So we already have this term and this term and S inverse. So we multiply the 3. So the first term, we have 6, negative 7, and 2. 6, negative 7, and 2 multiplied by the value of S inverse, which is a big number. You can try that one. Times minus 1, 1.5, and minus 2. So if you do this, this will give negative 1.6424. So this is the value of W. And now, since value W is less than 0, we allocate the vector X. 11, 13, 3, we allocate this to population 2. That is because the value of W is negative. So instead of allocating it to population 1, we assign it to population 2. There's some exercise on the same, unless there's a question. Do we have a question? Did you follow through?
Yes.
Did you follow through the example? Okay. So there's an exercise on the same. Now we are given x bar 1 from that population 1, x bar 2, and from population 2, and the sample covariance matrix is given by this. So you need to classify a vector x, a variable x, 34, 11, and 8, using the discriminant rule. And then there's a solution for that, so you can follow through and see how it goes. So that is all for today's lecture. And I think we are through with this course. So as I said, lecture 7, you're going to read on your own. Then I'll put some notes on discriminant, sorry, not discriminant, but class